Hello, so the title of my presentation is The Significance of the Accretion Contents of the White Dwarf GD424. So basically, what does that all mean? Let's start with some background information about white dwarfs themselves. So we basically all know that they're remnants of stars that have previously been within the main sequence. Usually stars that have a mass that is less than about 8 times the mass of our sun are the ones that turn into white dwarfs toward the end of their life. A white dwarf will often have about the mass of our sun, but still is only about the size of Earth, if not smaller. So this makes them one of the densest objects in the universe, only being surpassed by black holes and neutron stars. So a white dwarf's gravity at its surface is about 100,000 times greater than Earth's. So on the left here, we see a popular white dwarf, Sirius B, which, to compare, is 300,000 times more massive than Earth, even though it's even smaller in size. So around the white dwarf are various atoms. What elements tend to do is that the heavy elements sink to the center and the lighter ones rise up in the photosphere. So hydrogen and helium are the lightest elements, and those are the ones that we usually find in the white dwarf's outer atmosphere. This is really important because what we really only expect to see from a white dwarf are these lighter atoms around the photosphere. So when it's found that this is not the case, it means something strange is occurring, which becomes an important concept to know for the article. Because when unknown elements are around a white dwarf, we have to wonder, where did they come from? So white dwarfs are not able to create internal pressure because they're essentially a dead star. So internal pressure is usually caused by the release of energy from fusion, but this doesn't occur because fusion has ceased since the star has lost its fuel, and the white dwarf is simply just the remnant core of the original star. So this causes gravity to compact all of the matter inwardly until even the electrons are smashed right next to each other. So under normal gravitational circumstances, the behavior of subatomic particles, particularly electrons, is as follows. We all know electrons with the same spin are not allowed to occupy the same energy level of an atom. Since there are only 2 types of spin that an electron can have, only 2 of these different electrons can occupy the same energy level within the atom. And this is what we know as the Pauli exclusion principle. So once again, in normal circumstances, in normal matter, this is usually not of any particular significance because there's not enough electrons floating around, and there's not enough gravity to make things crowded. However, in a white dwarf, their matter is so much more densely compacted that these electrons are significantly closer together. The term used to describe this is degenerate matter, meaning that all the energy levels within the atoms are filled with their needed electrons. Now, a really important point here is that for gravity to compress the quite massive white dwarf any further, it would have to compress and place these electrons where quantum mechanically it's impossible to put them. So degenerate describes that since the subatomic particles, particularly electrons, it describes how they can get no closer to each other. So this forms a type of pressure that pushes outward, and in a white dwarf, it helps it push against gravity. So instead of internal fusion, this degenerate matter is what keeps the white dwarf from collapsing. So once a whole star is considered degenerate, gravity cannot compress it anymore because the laws of quantum mechanics prohibit this from happening. So this is the phenomenon that keeps white dwarfs from collapsing. Okay, so some terms we'll refresh on, or to at least clarify before we get into the article. You may have heard the word accretion in terms of astronomy in an accretion disk, which is usually around a star or a black hole. An accretion from a celestial body is the process of this gradual buildup around a massive body. So the meaning of accretion in context of this article is how much material is entering the photosphere of the white star, of the white dwarf star, And then the term diffusion is what describes the act of such material leaving the photosphere. So finally, on to the article. This article is about a specific white dwarf, GD424. The article states that in general, we expect certain elements to be present in white dwarfs, and we also expect to see these elements at certain concentrations. So when we either see elements in higher concentrations or elements that are not expected at all, we wonder where these elements came from. So GD424 was discovered to have metals and high amounts of hydrogen that come from sucking up a planet. The article authors used spectra and photometry to investigate more into the absorbed planet. To make more sense of their data, they had to come up with theoretical information for when the accretion started and how fast it occurred to make sense of what kind of planet had been near the star. In GD424's case, it is one of the fastest accretion times recorded for a white dwarf. So GD424 is a metal-polluted helium-dominated white dwarf. GD424 also contains a significant amount of hydrogen, causing this interest in investigating the scientific possibilities and characteristics of the star. So the main focus of the authors is to investigate the background of the stellar body's peculiar chemical composition and possibly also the makeup of the planet that it had absorbed. So a method used to collect the data was observing spectra and photometry using the William Herschel telescope that's located in Spain. After concluding that GD424 had a helium-dominated photosphere, they also discovered that not only hydrogen was present, but also high levels of oxygen, magnesium, silicon, and calcium. So what they used with the telescope was the intermediate dispersion spectrograph, an imaging system, which is also called ISIS, and all these observations were conducted under clear sky conditions. So here they graphed the composite average spectrum of GD424, and once they kind of understood what the white dwarf was accreting and understood the parameters, it also aided them in making sense of their collection for future data. So then they were able to move on to figuring out concentrations of the uncommon metals that were found. So they analyzed the absorption lines, and a spectrograph was used to analyze the spectra from the white dwarf. So they kind of showed a composite average of the spectra and measured the wavelengths of various elements in angstroms. The chart shows that the strongest absorbed elements were mainly helium and hydrogen, which is to be expected, but that it also contained the oxygen, magnesium, silicon, and calcium. So now they knew more about the contents and the composition, so they knew more about the planet that they were looking into, and they knew more about the contents in the photosphere of the white dwarf. And a photosphere is the area around a star where the star's light can reach and radiate. So now they wanted to use all this information to try to figure out more information about the planet. So other aspects of this astronomical investigation that they had to answer was the rate of accretion. They needed to determine when the accretion started and then how fast it was occurring. So another model was used by the authors to understand this phenomenon. The model was separated into 3 parts. First, there's an increase in accretion, which leads to an increase in the abundance of metals. And then second, the accretion rate reaches a steady state, which is the metals reaching an equilibrium in the photosphere. And then third, when the accretion begins to decrease, causing the metals to diffuse and sink into the white dwarf, leading to their decay and exponential rate. So basically, they were expecting the rate of accretion to follow this particular method. And basically figuring out at what point in this model the white dwarf was at in relation to its accretion was kind of uncertain. So what they did is that they tested in all 3 cases. So knowing which state the star was in was really important and useful because it helped them understand what kind of planet it was absorbing. So they graphed the concentrations of the elements from whatever planet, considering which rate the white dwarf was accreting. So they followed this model and graphed what the presence of elements would be, whether GD424 was at an increasing rate or a decreasing rate. So for the increasing and the steady rates, the inferred planet body was very similar and resembled other planets in that solar system. So it would make sense that the planet it was currently accreting was a dry planet, similar to Earth in its crust, but it just had more calcium. However, that was not the case for a decreasing state, because none of the minerals or the elements really matched anything else in that particular solar system. So basically, they found no planet composition in that particular area of space that would have made sense, considering the rates coming from a decreasing rate. So there wasn't a plausible parent body or planet that really would have made sense. So one thing that makes GD424 special is that it has one of the highest accretion rates found in any white dwarf. So the lowest amount of mass that GD424 is believed to have accreted so far is 7 times 10 to the 22nd grams, or 1.5 times 10 to the 20th pounds, or 7 times 10 to the 16th metric tons, however you want to attempt to visualize that. So another topic that was desired to be investigated by the authors about the accreting white dwarf GD424 was about finding out how much water was on this apparent second planet that the white dwarf had been absorbing, and I'll get into that in a bit. So they discovered that the spectra from GD424 had different elements. So basically these are the absorption lines, and then a best fit model was added to the graph. So at this point, they knew further about the composition of even the planet that GD424 was accreting. So they used high-resolution spectroscopy and also discovered other elements, including oxygen, sodium, manganese, chromium, nickel, silicon, iron, magnesium, titanium, calcium, aluminum, all of those. So basically at this point, they kind of already knew that they were dealing with a planet that was similar to Earth but had more calcium. So they feel like at this point that they understood the composition of this planet, but they discovered that there was an excess amount of oxygen and hydrogen. So the authors tried to get an idea of the water content that would have been on this very dry planet, and there were oxygen atoms that they were unable to account for in common dry minerals such as magnesium oxide or titanium dioxide. So, however, currently, GD424 was found to be accreting dry and rocky planetary pieces. So since this planet was believed to be dry and arid, so they didn't really have an explanation of where all this extra oxygen was coming from. So the next question that arose was, where did it all come from? So they discovered the first planet that they were aware of was this dry, rocky planet. So this strongly suggested that the extra hydrogen would have come from an entirely different astronomical body separate from the current planet that was being absorbed. So they were basically able to figure out that that meant there was a totally separate planet that also would have been quite water-rich, that was somehow destroyed, and its material somehow came to contact with GD424. So, in conclusion, we now understand that GD424 was a star that would have been categorized on the main sequence that then became a white dwarf, and then it began absorbing materials from a planet that had heavy quantities of water, and then moved on to a secondary planet that it's currently accreting, which is more dry and rocky. So GD424's chemical makeup in the article was investigated and measured, and it was found to be contaminated with metals. So this led to the idea that it absorbed components from a former planet. What kind of planet and what its own composition was also investigated. The method in which the authors did this began with estimating the photospheric concentrations of these metals by comparing them to the relative abundance of helium, which would be the normal main component of a white dwarf's atmosphere. The way the composition was measured by a combination of measuring spectra and surveying the photometry of the white dwarf. And so it's expected that GD424 will continue accreting planets if they or their materials come close enough to the white dwarf's photosphere and gravitational field.